Look at anything around you right now. Your phone, your hand, the air you are breathing, the coffee going cold next to you. Every single one of those is made of the same kind of tiny building blocks, following the same small set of rules. That is the secret chemistry never quite tells you up front. It is not a random list of symbols and reactions to memorize. It is the rule book for what everything is made of and how it changes. And once you see the rule book, the whole subject stops being a wall of vocabulary and starts being one connected picture. Most people leave chemistry class remembering a few scary words: moles, valence, stoichiometry, words with no map. So here is what we're going to do. We are going to build chemistry from the ground up in the right order, starting from the smallest piece of stuff and working our way up to the reactions happening inside your own body. By the end of this video, you will understand what chemistry is actually about, and every one of those scary words will finally have a place to sit. Hey, it is Daniel from Simplex Academy. If you like hard subjects explained clearly and calmly, the way they should have been the first time, subscribe and stick around. Let's make chemistry make sense. First, why should you care? Because chemistry is not stuck in a lab. It is cooking your food, charging your battery, digesting your lunch, cleaning your kitchen, and keeping you alive every second. Why soap removes grease, why bread rises, why a battery dies, why rust eats a car, why medicine works. Every one of those is chemistry. Learn the rule book, and the physical world turns from random to readable. So let's start with the one sentence that holds the whole subject together. Chemistry is the study of matter and how it changes. That is it. Matter is just a fancy word for stuff. Anything you can touch, anything that takes up space and has weight, is matter. The air, the water, the phone, you. So when we study chemistry, we are really asking two questions. What is stuff made of, and what happens when stuff changes? Hold on to that. What it is made of, and how it changes. Now, where do we begin? With the smallest piece. If you took anything, say a drop of water, and kept cutting it in half, again and again, you would eventually reach a piece so small you cannot divide it any further and still have that thing. That smallest piece is the atom. Atoms are the letters of the entire physical world. Everything is spelled out of them, and they are unimaginably small. There are more atoms in a single glass of water than there are glasses of water in all the oceans on Earth. That's small. So what is an atom made of? Here is where it gets beautifully simple. Every atom has a tiny, dense center called the nucleus, and around it, a haze of even tinier particles called electrons. The nucleus is built from two kinds of pieces: protons, which carry a positive charge, and neutrons, which carry no charge at all. And the electrons buzzing around the outside carry a negative charge. That is the entire cast: protons, neutrons, electrons. Positive, neutral, negative. Now, quick honesty, because this matters. You have probably seen atoms drawn like a little solar system, with electrons looping around in neat circles. That picture is a useful cartoon, but it is not quite true. Electrons do not travel on tidy tracks. They exist in a kind of fuzzy cloud of probably here, maybe there. For today, the cartoon is fine, as long as you know the real thing is blurrier. Keep the picture. Drop the certainty. Here is the single most important fact about atoms, so let's slow down. The number of protons in the nucleus decides what kind of atom it is. 1 proton, and it is hydrogen. 6 protons, and it is carbon. 79, and it is gold. Change the proton count, and you literally change what substance you are holding. That number is the identity card of the atom, and that gives us our next word. An element is just one pure type of atom. Gold is an element because every atom in it has 79 protons. Oxygen is an element. Carbon is an element. There are about 118 known elements, and that is the entire supply of raw materials for the whole universe. Everything you have ever seen is built from that one box of about 118 letters. Let's pause and lock in the map so far, because these first links carry the rest. Matter is stuff. Stuff is made of atoms. An atom is a nucleus of protons and neutrons wrapped in a cloud of electrons, and the number of protons decides which element you have. Atoms are the letters. Elements are the different letters in the alphabet. Now, if you have about 118 letters, you would want to organize them. And chemists did. into the most useful chart in all of science, the periodic table. You have seen it, that grid of boxes on the classroom wall that looked like a random mess. It is not random at all. It is the elements lined up in order of how many protons they have, and then folded into rows and columns so that similar atoms line up together. So what makes the table so powerful? The columns. Elements in the same column behave in similar ways, and here is the reason why, which ties back to electrons. The electrons on the outer edge of an atom are the ones that do all the interacting. Chemists call them the outer electrons. Atoms in the same column have the same number of outer electrons, so they tend to react in the same way. That is why the table is not a list to memorize. It is a map. If you know where an element sits, you can guess how it will behave without ever having met it. That is the whole point of the chart. Here is a quick taste of that power. Look at the very last column on the right. Those elements, like helium and neon, already have a full outer ring of electrons. They are perfectly content, so they almost never react with anything. We call them the noble gases, and it is why the helium in a balloon just floats there doing nothing. Now look at the very first column on the left. Those atoms each have a single spare outer electron they are desperate to lose, which makes them wildly reactive. Same chart, two edges, opposite personalities, and you could predict both just from the address. So why do atoms bother interacting at all? Why not just float around alone? This is the heart of chemistry, so let's get it right. Atoms are, in a sense, chasing stability. An atom is most content when its outer ring of electrons is full. Some atoms have a nearly full outer ring and just need a little more. Others have one or two spare electrons they would happily get rid of. And when a needy atom meets a generous one, something clicks. They connect. That connection is called a chemical bond, and it is the reason anything in the universe sticks together at all. There are two main ways atoms bond, and the difference is simple. Sometimes one atom straight up gives an electron to another. The atom that gives becomes slightly positive. The one that takes becomes slightly negative. And because opposite charges attract, they lock together. That is an ionic bond. Other times, two atoms cannot bear to give an electron away, so they compromise and share a pair of electrons between them, like two people holding the same rope. That is a covalent bond. Giving, or sharing, that is basically all of bonding. Let me make that real with the most famous example there is. Take sodium, a soft metal so reactive it bursts into flame in water, and take chlorine, a poisonous green gas. Sodium has one spare electron it wants gone. Chlorine needs exactly one. So sodium hands its electron to chlorine, the two become oppositely charged, and they snap together into a bond. And the thing they make is table salt. The stuff on your fries. A violent metal plus a toxic gas becomes something you sprinkle on dinner. That is the magic you have to sit with. When atoms bond, the result can be nothing like the ingredients, and that leads straight to the next word. When two or more atoms bond together, you get a molecule. If those atoms come from different elements, the molecule is also called a compound. Water is a molecule. Two hydrogen atoms sharing electrons with one oxygen atom. And water behaves nothing like hydrogen, which is explosive, or oxygen, which feeds fire. Bonded together, they make the thing that puts fire out. So here is the deep idea. The properties of a compound are brand new. They are not the average of the parts. They are something genuinely different that only appears once the atoms join. Let's take a breath and look at the map, because we have quietly built a lot. Atoms are letters. Elements are the alphabet, organized on the periodic table. Atoms bond by giving or sharing outer electrons, and bonded atoms make molecules and compounds with brand new properties. So far, this is all about how stuff is put together. Now we get to the second half of our definition, how stuff changes. When substances actually transform into different substances, that is a chemical reaction. And here is the one rule that makes reactions make sense. In a reaction, atoms are never created and never destroyed. They are only rearranged. Think of the atoms as a set of building bricks. A reaction takes the bricks apart and rebuilds them into something new, but every brick is still there. Nothing vanishes. Nothing appears from nowhere. This is called the conservation of mass, and it is one of the most reliable rules in all of science. So what does a reaction look like? Take hydrogen gas and oxygen gas, give them a spark, and the atoms come apart and rebuild themselves into water. The exact same atoms that started as two invisible gases end up as a liquid. Count the atoms before, count them after, and the numbers match perfectly. That is why chemists balance equations. Balancing is not some arbitrary math trick. It is just bookkeeping to make sure every atom that went in also comes out. Same bricks, new build. Now, here is a fair question, and it is the one that trips up almost every beginner. If atoms are so unimaginably small, how does a chemist actually work with them? You cannot count out 3 atoms with tweezers, and this is where that scary word, the mole, finally makes sense. A mole is simply a counting word, like the word dozen. A dozen always means 12. A mole always means a specific, gigantic number of particles, about a 6 followed by 23 zeros. Chemists picked a number that huge because atoms are so tiny that you need an enormous pile of them before you have enough to weigh and pour. So when a chemist says 1 mole of carbon, they just mean a countable, weighable handful of atoms. The mole is not advanced math, it is a chemist's dozen. That is the whole idea. Let's do a quick recap because reactions are the turning point of the subject. A reaction rearranges atoms into new substances. No atom is ever lost or created, which is conservation of mass. Balancing an equation is just counting atoms on both sides, and the mole is simply a big counting unit that lets chemists measure out atoms in real amounts. Rearrange, conserve, count. Now, reactions do not just move atoms around, they also move energy, and this is the next link. Every bond stores a little energy, and breaking or making bonds either releases energy or soaks it up. When a reaction gives off energy, usually as heat or light, we call it exothermic. A fire is exothermic. That warmth and glow is energy escaping as bonds rearrange. When a reaction instead absorbs energy from its surroundings, we call it endothermic. An instant cold pack is endothermic. It pulls heat in and gets cold in your hand. And there is one more piece to energy. Most reactions do not start on their own, even when they want to. A log will happily burn, but it will sit in your fireplace forever until you give it a spark. That first push needed to get a reaction going is called activation energy. The match provides it. This is why the whole world is not spontaneously on fire, even though so much of it could burn. Everything is waiting for its spark. So energy is the second half of every reaction. Atoms rearrange and energy flows in or out. Energy also decides something you see every single day, whether a substance is a solid, a liquid, or a gas. And here is the surprise. Ice, water, and steam are all the exact same molecules. Nothing about the chemistry changed. What changed is how much energy those molecules have. In a solid, the molecules are low on energy, packed tightly, and can only jiggle in place. Add heat, and they gain enough energy to slide past each other, and you get a liquid. Add even more, and they break loose completely and fly around freely as a gas. So solid, liquid, and gas are not 3 different substances. They are the same substance at 3 different energy levels. That is why a single ice cube can become water and then steam without ever stopping being water. Now let's zoom into one special family of reactions that runs through your whole daily life. Acids and bases. You already know these words from lemon juice and soap, and the idea underneath is simple. An acid is a substance that releases a particular particle, a hydrogen ion, when it dissolves in water. A base is the opposite. It soaks those particles up. To measure where something falls, chemists use the pH scale, a simple dial running from 0 to 14. 7, right in the middle, is neutral, like pure water. Below 7 is acidic, like lemon juice or vinegar. Above 7 is basic, like soap or baking soda. Why does this matter to you? Because acids and bases are everywhere, and they explain a lot. Your stomach uses a strong acid to break down food. Baking soda, a base, reacts with the acid in a recipe to make the bubbles that lift a cake. And when an acid and a base meet, they cancel each other out and calm down, which is exactly what an antacid does to a sour stomach. One quick but important note. Strong does not mean the same thing as dangerous. Lemon juice is an acid and it is fine. A drain cleaner is a strong base and it is not. Strength is about how completely something reacts. not about how scary it is. Before we wrap up, let me show you the rulebook running in your actual day, because this is where it all pays off. When you charge your phone, you are pushing a chemical reaction backwards to store energy, and when you use it, you let that reaction run forward to release the energy again. That is all a battery is. When iron rusts, iron atoms are slowly bonding with oxygen from the air into a brand new compound, which is why rust looks and feels nothing like clean metal. When you cook, heat drives reactions that rearrange the molecules in your food, building hundreds of new ones, which is where browning and flavor come from. And it is why you can never uncook an egg. And soap works because its molecules have one end that grips water and one end that grips grease, so they drag the grease off your hands and away. None of that is lab magic. It is the same handful of rules you just learned, quietly running your life. All right, let's bring the whole subject together, because you now have the full map in your head. Let me clear up the mix-ups that confuse almost everyone now that each word has a home. First, atom, element, molecule, and compound are not four random terms. An atom is one building block. An element is one pure type of atom. A molecule is atoms bonded together. A compound is a molecule made of different elements. They are just different zoom levels of the same idea. Second, the word chemical does not mean dangerous or unnatural. Water is a chemical. Oxygen is a chemical. You are made entirely of chemicals. The word just means matter. And third, when something burns away to almost nothing, the mass did not vanish. It floated off as invisible gases. Weigh everything, including the air, and it all still adds up. Conservation of mass. Every time. So here is the whole rulebook in 1 minute, the part worth keeping. Chemistry is the study of matter and how it changes. First, all stuff is made of atoms. Second, an atom is a nucleus of protons and neutrons surrounded by electrons, and the proton count decides which element it is. Third, the elements are organized on the periodic table, where columns share behavior because they share outer electrons. Fourth, atoms bond by giving or sharing those outer electrons, forming molecules and compounds with brand new properties. Fifth, reactions rearrange atoms into new substances without ever creating or destroying a single one, and we count them in moles. Sixth, every reaction moves energy, releasing it or absorbing it, and needs a spark of activation energy to begin. And seventh, acids and bases are a special everyday family of reactions measured on the pH scale. That is general chemistry connected in one breath. That is the whole subject, from a single invisible atom all the way up to the reactions cooking your food and powering your phone. Not a pile of symbols, one connected rule book for what everything is made of and how it changes. And once you can see the rule book, every formula and every reaction you ever meet after this has a place to belong. So here is my question for you. Which piece do you want to zoom into next? How the periodic table really works, column by column. What the mole actually is, with real examples. Or how bonds decide whether something is a solid, a liquid, or a gas. Tell me in the comments, and I will build that one next, just like this. I am Daniel, thanks for watching, and I will see you in the next one.